Hi guys, welcome back to Math 135. Today we're talking about graphs and functions still, chapter 1, and in particular transformations of functions. So in the last class, we established the library of functions, basic ones, and in this class we're talking about how to move them around and stretch them out, flip them over. That's all these kind of things. Those actions, we call those transformations because you're transforming the original graph. And there's three main categories, the numbers 1 through 3 right here. The first is vertical or horizontal translations. Translations, another word for translation is a shift. You see the word down here, shift. And that's the first type of transformation. Second type of transformation is stretching or compressing. Stretching out, you can stretch out either horizontally or vertically, stretching up and down or left and right. We also call compressing shrinking. And then the last type of thing we're learning today is reflections. Reflections, just like it sounds like, you reflect something over the x-axis or y-axis. I think of reflecting over the x-axis as like a vertical stretch because you're flipping it up and down, and then a reflection over the y-axis like a horizontal reflection because you're flipping left and right. Okay, and then lastly, we're gonna learn how to just put all those different transformations together. Okay, really cool, useful section, I think. Last section and this section combined really are super powerful sections because it gives you all the basic functions and all like different forms of them. And knowing how to transform functions really super key in helping us move around our graphs or to graph more complicated things. Okay, so let's go. Number 1. This video, I'm hoping you get through numbers 1 and 2 in this video, but try to keep it to 20 minutes, around 20 minutes. Okay, number 1, use horizontal or vertical translations to graph functions. Translation, remember, just another word for a shift. So here we're given a function y equals f of x, that's your starting function. And if you add a number at the end, it just moves it up. And if you subtract the number, so if this d is negative, it moves it down. So it just moves it d units in the y direction. And that d could be up or down. If it's negative down, positive is up. Okay, y equals to f of x minus c. So if the number that you're adding or subtracting is inside of the parentheses, so f is like applied to it after the subtraction or addition has already taken place, then in that case you shift left or right. Now, here's the thing. If it's minus a number, that's a shift to the right. And if it's a positive number, it shifts to the left, which to me is a little counterintuitive because like the y direction was really straightforward, right? D, if it's positive, you move up, negative move down, that makes sense. Here, if you have a negative number, it actually moves to the right. Now, if you think about it long enough and carefully enough, it will make sense to you, but just intuitively to me, it doesn't make sense. So yeah, just a thing to remember. When you minus number, left. I'm sorry, I said that wrong. Minus number to the right, and then plus number to the left. Okay, we're gonna try our questions 1, 2, 3 right now. So yeah, let's just do that real quick. And you'll notice questions 1 through 9, they're all different forms of one of our favorites, the quadratic. What do we call that thing? It's a squared function, also called this quadratic function. And we're looking at the basic quadratic. So question number 1, we're just graphing these things, and I'm just gonna do a rough sketch. Number 1, this should be a review from last time. Here's your x-axis, here's your y-axis. X squared, remember it starts in the middle. You go 1 out and 1 up on either side. And then you go 2 out, 2 squared is 4, so you go 2 out and 4 up on either side. And that gives you the shape of a parabola. Oh, missed. Maybe that's kind of small, so it's harder to hit it, but okay. Okay, so that's the initial function, right? Number 1. Number 1 done. Okay, number 2, x minus 3 squared. So remember what we were saying? Minus 3, that moves it to the right. Now, here's the thing. Why does it move to the right? Why to the right? Well, here's why, because just think about a table real quick with me. Let's make a nice table. I said a nice table. Okay, so if you think about some x, y values. Okay, first of all, 0, 0. If I plug in 0 for x, that's where you would have normally started at 0, 0, right in the center. If you plug in 0 for x here, though, you got a minus 3, and then it's squared. So that means 0. Actually, no, I don't want to start with 0. I will get to 0 eventually. Let's start with 3 instead. Why did I start with 3? Well, 3, if I plug in 3 here, that's what makes this inside 0. Right? So if I have the inside 0, then I square it, I get 0. So if I plug in a 3, I get y as 0. 0 squared is 0. And now we see y is shifted to the right because the x value that makes this inside thing 0 like I want it to be is actually a positive 3 because I'm subtracting 3, so x must have been a positive 3. So here's 1, 2, 3. That means your new position starts to the right, which is why when you subtract a number inside the parentheses, it moves it to the right side. And that same principle applies no matter what function you're dealing with. Okay, now let's say I plug in something that's 1 to the left of 3. Well, that's the same relative position as 1 to the left of my starting position from 0, right? So that means from here, left 1, up 1, that's going to be your next point. In this case, that number is 2, and 1 to the right would be 4. So 4, that's left 1, up 1, right 1, up 1. And if I go 2 out, that's going to give me to 1, right? So if I go 2 out from this starting position 3, that's at 1. 2 out from the starting position of 3 is 5 on the right-hand side. And so I should go 1, 2 out, and 4 up. 1, 2, 3, 4. Right, like that. So you see it's the same shape, exact shape, right? But it's just shifted over. I should use a different color. So in blue is problem number 2 graphed. Same shape, just shifted to the right. Okay. Oh, I said I was going to do 0. Yeah, let's do 0. If I plug in 0, 0 minus 3, and then square that, I get 9. That's going to be 9. 4, 5, 6, 7, 8, 9. It's over there. Okay, so then this would have gone something like that. Okay, but enough with that graph. Let's move on to the next one. So I want to do number 3 now. And yeah, okay, let's do number 3. Okay, so now this is actually easier one. You have x squared, that's the original function, and then you're just adding 1 at the very end, right? So adding 1 at the very end, that takes your whole graph. Mind you, just what that graph originally looked like. I shouldn't have erased that one. Something like this, right? And then all I'm doing now is I'm adding 1. So adding 1 just moves everything, all the y values up by 1. So simple, very simple. It's just shifting up. So that is your new position there. Yeah, so oops, I shifted 2 up, sorry. Should have only shifted 1 up. So right there. Yeah. Now, if you were to graph it from scratch, what would you do? You take your initial point of 0, move it up 1. From there, go right 1, up 1, left 1, up 1. Right 2, up 4. 1, 2, 3, 4 puts you right at 5. Left 2, up 4, that puts you right at 5. This is 5. Okay, that's it. So that's 1, 2, 3. Let's move on to the next type of transformation. So those are translations, or also called shifts. Now we move on to vertical stretching and horizontal stretching. Stretching or compression. We call when you're making it smaller, we call it compressing or shrinking. Vertical stretching, compressions. Sorry. Again, we start with our original function y equals f of x. And then let's say you're given a number that's bigger than 0. Why bigger than 0? Well, because if it's less than 0, that makes it negative. And if it's negative, that's actually the third type of transformation. It's a reflection. So we're dealing, for now, in number 2, just with positive values. And what happens if you take that positive value and you just multiply it at the end by whatever your function was? That's going to be a vertical stretch if your number is bigger than 1. So like the typical example I think of is 2. What if it's 2? A is 2. 2 times f of x means you're just doubling everything, right? You're making it go up twice as fast as it would have. And then on the other hand, if you have something that's less than 1, then that's a shrink. F is shrunk or compressed. And then I think of the standard example as like a half. What if A is a half? Then you're just halving all your heights, right? So you're shrinking it, compressing it downwards. Now note, when you're shrinking, we sometimes call this A that you're multiplying by the scale factor. And it's just a result of multiplying the original y values by that number. Okay, on to horizontal stretches and compressions. Now to me, like the horizontal things are always kind of counterintuitive. Like we saw in the last one, when you subtracted a number, it moves you to the right, yeah? And same if you plus it, it moves you to the left. Well, here, check out horizontal stretching and compressing. Start with our original function. Again, you have some value that's bigger than 0, because otherwise it would be a reflection as well. And if that number is bigger than 1, this time you're shrinking. F of b of x is shrunk. Now, where does that b go? That b goes this time inside of the parentheses. So before the function is even applied, inside the parentheses, it's already multiplied by b. Okay, and if it's bigger than 1, it's shrunk. So if b is 2, it actually shrinks it. Well, but it shrinks it horizontally. So that means if you look at the graph, try to think of a graph with me. Like, let's take a parabola graph. If I have a parabola graph and I shrink it horizontally, so I bring these guys inside, it's going to look something like this, right? And that, to me, it looks actually it looks like a vertical stretch, actually, right? So really, horizontal shrinking is very synonymous or similar to vertical stretching. Okay, and then on the other hand, if you're... Oh, I'm sorry, this is a typo. Sorry, guys, this should have been B. I'll change it again in the notes before I put it out to you. This is going to say B on your notes. So if B is less than 1, then it should be stretched horizontally. Stretched, so that means it's widened if B is less than 1. So that's the kind of counterintuitive part. Now here's a note. When stretching compressing, you multiply the original x values by 1 over B. 1 over B. It's kind of like backwards, like I was saying, right? And I know it seems weird, but same thing. Like if you think about it long enough, just like how if we thought about the horizontal shifts, if we think about it long enough, it will start to make sense. Sorry, I'm talking too long. Let's get to the questions as soon as we can. So let me just wrap this up. Note horizontal transformations feel counterintuitive. That's the same thing I said already. All right, let's get to questions 4 and 5. And then we'll be done with this first video. Okay, so here it is. And again, I want to keep my original function in mind. So actually, let me move this up here. And if you remember the original function, let's clean up the extra mess here. Was a parabola, right? The original f of x equals to x squared. And it was a parabola starting from 0, 0, yeah? And then we went out 1, up 1 normally. Now, what happens if you do 2x squared? So this is the case, the x squared the function already is applied here. And then at the end, you're multiplying by 2. So this would be a vertical stretch by 2. So this is like your A is equal to 2 here. Okay, so what does that do? Well, normally, you still start at the same spot. Normally, you go out 1 and up 1, right? Well, if you're stretching by 2, that means you're going to go out 1 and up 2. Double. Just like that. And then same thing in both directions, right? So I'm going to go out 1 to the left here. And then instead of going up 1, I'm going to go up double, up 2. Okay, normally when I go out 2, I would go up by 4, right? 1, 2, 3, 4. But this time I'm doubling it, so I go out 2. I should go up by 8. So out 2, up 1, 2, 3, 4, 5, 6, 7, 8 right there. So this is where I'm landing here. Okay, so out 2, up 8. That puts me in this position right here. And then same thing for the left side, right? Out 2, up 8. So out 1, 2, and up by 8. That puts me right over here. Okay, so now connecting the dots. You see how it's stretched vertically compared to the original graph. Original graph would have looked more like this. Actually, it's kind of drawn poorly. Look more like something like that, yeah. So let me redraw the original graph to compare. So original graph would have been here, here, 1, 2, 3, 4, here, and 3, 9, something like this. Something like that. Okay, so you see how it's stretched vertically, right? Compared to the original. Okay, now on to number 5. So number 5 here, this time, the inside is being multiplied before the function of squaring happens, right? So here you have b equal to 2. B equal to 2. Which means you have a horizontal shrink. You got horizontal shrinkage. Okay, so that means, let's erase that one right there. I'm gonna keep my original graph, the x squared graph. This is y equals x squared, original. Okay, now what's happening here? You're changing the horizontal direction by a factor of 1 over b. Remember? So what does that mean? Okay, that means normally if I go out 1, up 1, right? But I'm gonna think about that backwards. I'm gonna think normally I go up 1 and over 1, right? But in this case, I'm gonna go up 1 and over, so 1 over b is equal to a half, right? So I'm gonna go up 1 and over just a half. So that's gonna put me right here. Oh, shoot. So it's gonna put me right at this spot here. And up 1 to the left, normally I go up 1. I'm gonna go this time a half. Okay, and then up 2, normally, or actually no, I should say up 4. Normally up 4, I would go out by 2, right? Because you remember this point? This point was 2 comma 4. 2 comma 4. But this time I'm gonna go up 4. I'm only gonna go out 1. And same thing on the left. This point here was negative 2 comma 4. This time I'm gonna go up 4, but I'm gonna go only out 1 to negative 1. So this, I'm shrinking horizontally. I'm bringing these guys in, right? Oh, I was supposed to use a different color. Sorry. Let's use purple this time. So I'm shrinking it horizontally, but if you look at the end result, it's actually the same as if I was to extend or to what's the word? Stretch vertically. Now, why is it the same as stretching vertically? But think about this. What happens if you square that? That's going to be 4x squared, right? So actually, you could, in this particular case, you could convert it and notice that that's actually a stretch. Yeah. Okay. Now, as I'm going through this, I'm showing you how I think about this. If it's confusing for you to think of like the movement the way I think about it, then you can also just resort to tables and resort to thinking about, okay, what happens to individual points. So I'm looking at this thing here. I know the starting position is still at x equal to 0. So let's start with that. At x equals to 0, then this guy, if I plug in 0, it's going to get 0 squared, still 0. So that's safe, right? Still there. And then just go out to the left and right. If I move it to x equal to 1, this is going to be 2 squared. That's going to give me 4. And oh, look, that's the point I had earlier, right? You could go out another one time. Let's say I plug in x as 2. Oh, I'm sorry. I said 1, 4, but also negative 1, 4, right? If I plug in a 2 or a negative 2, this is going to be 4 inside here or negative 4. And I square that, I'm going to get 16. So if I go out 2, I'm all the way at 16. It's like up here. Right, so there you have 3 points for either side of your parabola. Okay, something like that. I mean, just imagine I'm drawing this nice. Okay, that's it for stretching and for translations. So right around 20 minutes. Mark, let's stop this video here.